Okay, so welcome everyone to today's 1W-MINDS seminar this week. And today it's my great pleasure to have Professor Jonathan Scarlett. Professor Scarlett received a PhD degree in information engineering from University of Cambridge in 2014, and he is currently an assistant professor of mathematics at the National University of Singapore. So his research interests are in theoretic and algorithmic aspect of statistical influence, learning, and optimization, with a particular emphasis on information theoretical methods and analysis. He has received several awards, including Singapore National Research Foundation Fellowship. So today he will talk about beyond sparsity, compressive sensing with deep generative modeling assumption. So now the stage is yours. Thanks.
Okay, thank you very much. Yeah, I'm very happy to be here to participate in this very nice seminar series. So thank you for the invitation. This talk will be kind of half a broad introduction to the topic and half specifically about one of my papers with my postdoc, Jiacheng Liu. So the early parts will be a bit more like tutorial-like. Please feel free to ask questions either on the chat or unmute yourself along the way, or save them to the end as you prefer. I'm very happy to answer them either way. So yeah, there's a lot to unpack in this title. Let me start with a bit about generative modeling, because this has been a pretty hot topic in machine learning. And when you hear about generative modeling, you usually see these cool kinds of pictures, which are faces that were generated by a neural network, but they're actually fake. So these are not real images of people. These are fake generated images. The network itself was trained using a bunch of real images, but then the network was able to produce fake ones without cheating or anything. It's not like you're copying something in your training data and adjusting it a little bit. These are like genuinely different faces from those in the training set. And it's actually quite amazing how realistic they've become. Even in 2018, there's no way I could distinguish this from an actual photo myself. There's been other uses beyond just generating faces. People have made neural networks to generate artworks. There's been more application-driven things like text-to-speech, natural language processing, and it's not all about images. So yeah, a couple of these are about text. There's also things like music that generative models are producing. So yeah, this is all very cool. And this talk will be perhaps about an application of deep generative models, which is less immediately obvious, but still potentially very useful. And to get into that, I'll need to explain the other part of the title, which is linear inverse problems. Okay. So linear inverse problems, I'm sure many of you are familiar with, especially if you've heard of things like compressive sensing. Here is a simple illustration where we have an unknown vector. I've written sparse here, but just think of it as a general vector for a second. And we'd like to estimate the vector or know something about the vector, but we don't observe it directly. We only observe compressed samples of it. So if we're talking about linear inverse problems, we can represent that by multiplying by a circled measurement matrix. Common choices might be like IID Gaussian, but I'll talk a bit more about that in a second. So we're essentially getting some reduced version of the vector. It may also be noisy, so we're not getting perfect samples. And given the measurement matrix and the samples, which is A and Y, we would like to estimate X accurately. So classically, this is just like linear regression. And for classical linear regression, we should really hope that we have more M much larger than N. So essentially more equations than unknowns, or more samples than we have things that we're trying to estimate. And this big shift in compressed sensing, which is now been going on for at least 15 years, was that if we assume some structure on this unknown thing we're trying to estimate, we can actually get away with much fewer. We could actually have M much smaller than N, which is why I've drawn a sort of wide matrix here instead of a tall one. And the most famous example is sparsity. If the vector that you're trying to estimate is sparse, mostly the entries are 0 and only a few are non-zero, then the typical scaling you'll get is k log n, where k is the sparsity. And yeah, instead of this n type dependence on the number of coefficients, you're only getting log, which is of course much, much smaller. So yeah, there was this whole decade of very intensive research, and it's still going on today. And people have also looked beyond sparsity, which I'll talk about. Today, I'd like to give a bit more of a modern view of this problem, which is that we can use this idea of generative modeling. If we have an accurate data-driven generative model, then perhaps we can actually still do a lot better, even compared to the standard sparsity assumption. That's the rough idea behind the topics of this talk. So I guess we should ask why we might want to go beyond sparsity. And basically, the answer is that sparsity captures some, but not necessarily all of the structure in typical data sets. So one of the proposed applications of compressed sensing was medical imaging. So this is an MRI scan of a brain, and this is its Fourier representation. To avoid confusion, I should say that, like, when I say sparse vector, it could also be like a matrix. Like an image is more natural to think about as a matrix. So if you'd like, you could take that matrix and vectorize it, like stack all its rows or columns together to form a long vector. But the point is, if you have like some sort of linear measurement, it doesn't really matter whether it's a vector or a matrix. So hopefully that doesn't cause confusion. The other thing is that, like, the signals that we're looking at are not necessarily sparse in their natural domain. Like, this picture of the brain is not particularly sparse. Where you might tend to observe sparsity is when you view it in a different representation. So for example, if we look at Fourier domain, it does seem to be very sparse. Most of the energy is concentrated near the center. And you can see already that sparsity doesn't really capture everything, because sparsity would just suggest that some arbitrary fraction of this Fourier space is like non-zero, and the rest is zero or very close to zero. But you can see it's much more specifically structured than that. All of the energy appears to be near the center, which actually corresponds to lower frequencies. There have of course also been many efforts to incorporate these refined notions explicitly, things like structured sparsity. But even so, it seems that there may be some limitations into what you can really explicitly say with very explicit mathematical models. Not to rule out this approach altogether, but the idea of this talk is that perhaps we can also consider data-driven models. And data-driven models naturally can be much more targeted to the specific type of signal or data that you're looking at. So yeah, for example, if you had a whole history of brain scans that you've done, you could train a generative model to have a pretty good idea of what a typical brain scan looks like. And of course, the modern approach to doing that is with deep neural networks. So I'm not going to go into like the inner workings of these generative models or how you train them and things like that. That's a topic for another talk. But the very rough structure is like this. It has a low input dimension. So think of this K. This K is different from the K in the sparsity type of model. K here is the dimension of the latent variable. So we think of a relatively small latent variable being passed through a neural network, which produces a larger dimensional. Here I've depicted it as a vector, but again, it could be two-dimensional, so it could be an image. The neural network needs to be trained, which I won't go into, and you need to choose the architecture and everything like that. But for the purposes now, let's just say we've already got a very well-trained model which accurately represents the data that we're interested in. And then the idea is that as we vary all these Zs, we get to see all these different variations of whatever the data is representing, like faces or brain scans or anything else. Okay, so yeah, we can be much more data specific or application specific rather than trying to get these like general wide-reaching explicit models. This can come at a price. There can be issues with things like representation error, which I'll talk about throughout the talk. Okay, there are many types of linear measurement models. So I'll just talk a bit about what this measurement matrix might be, like what sort of measurements it might be capturing. And don't get confused, the measurement model is different from the generative model. The generative model is typically very, very, very nonlinear, but the measurement model, so yeah, the generative model is how we model this vector over here in the first place. But the measurement model is like what sort of measurements we see when we're observing the underlying signal. Hopefully that's clear, this distinction between measurements and generation. So in terms of measurements, we could talk about things like inpainting. So here's an image with a bunch of pixels removed. Maybe we'd like to fill them in, or like this can come up when you take a photo, but there's something in the photo you don't like. So you sort of erase it, but then you'd like to fill it in with something better. So inpainting has certainly undergone some advances recently following these neural network approaches. Like if you think about a classical method, there's probably no way it could have guessed what was between these gaps. Thanks to these generative models, we now can. Also things like denoising. So maybe we don't just have to talk about matrices that compress. We could talk about having as many observations as unknowns, or say one observation per pixel. But it may be that those observations are very noisy, like in this left image. So of course, we would naturally like to be able to denoise in scenarios where we have a noisy observation. And there's many like related tasks like super resolution, essentially converting a low resolution image into a high resolution one without losing as little quality, or like maintaining quality as much as possible. Classically, it sounds kind of impossible, but again, thanks to generative models, we can do this remarkably well. And things like deblurring, if you have a blurry image and you want some way to get rid of the blur and make it a sharper image. And it may just be like a regular reconstruction problem. So going back to the MRI example, MRI machines, I wouldn't say I'm an expert on this. MRI machines don't observe pixels directly, they observe Fourier measurements, hence why we showed the Fourier transform here. And they don't measure every single Fourier entry, because that would mean the MRI scan would be really long. So they observe some, but not all of the Fourier space. And from that, we would like to be able to accurately reconstruct the image. So these examples are quite practical and specific. A lot of this talk will be more on the theoretical side. And when it comes to theory, probably the most common type of measurement is IID Gaussian. So going back to this image where you've got your measurement matrix, which is determining like the linear transformation. Okay, I'm very sorry. I will have to pause for a second. Okay, I'm really sorry about this. I'll be back very, very soon. Okay, I'm very sorry. The rest of the talk will be uninterrupted. So in this linear model, the IID Gaussian measurement is just where every one of these entries is generated at random from a Gaussian distribution. And basically, it's probably more for theoretical purposes because it's very easy to analyze theoretically. But it can also have some practical applications, because there are some applications where you're lucky enough to have complete control over how you choose your measurements. Like you might be actually building a sensor and you get to choose how that sensor actually takes its measurements. So in that case, things like IID Gaussian can be used. But this caveat should be kept in mind that in things like MRI, you need to be taking Fourier measurements, which is different from IID Gaussian. Okay, any questions? Feel free to type. I don't see any so far, so I think I'll continue. So the other ingredient of all these compressed sensing problems, both with sparse priors or generative priors, is once you obtain these measurements, like once you obtain Y, how do you actually recover X? And remember, A, the measurement is assumed to be known. So yeah, you know the linear transformation, like you know which pixels are observed, which are unobserved, or you know which Fourier measurements you've taken. So you know A, but you want to recover X. Okay, so let's first talk about sparsity. So let's say that X is known to be sparse, and we have this sparse prior assumption, and then we'll get to generative priors in a second. Perhaps an idealized problem that you might solve in the sparse case is try to get the sparsest signal that is consistent with the measurements. If it was noiseless, you might say subject to Y equals AX. But if you're noisy, you wouldn't really expect Y to exactly equal AX anyway, because there is noise. So if there's noise, you'll probably more likely introduce this epsilon parameter to say, let's let's allow a bit of back off from that. So there's a few problems with this idealized problem, the most obvious of which is that it's very computationally difficult. It's a combinatorial optimization problem because sparsity is like a very combinatorial property. If you change one entry of your x from 0 to like 0.0001, the sparsity changes by 1. It's very discontinuous and not very nice to work with. So there was this very long line of works, or very extensive line of works on convex relaxations, starting with Donahoe, Candace, and so on, where the instead of minimizing sparsity, you minimize a convex surrogate for sparsity. And the one norm is the famous one. So I won't go into a lot of detail, but essentially one norm serves as a proxy for sparsity. It has these nice geometric properties which sort of favor sparsity, but it doesn't have this this like very nuisance issue of like non-differentiable and like not having well-defined gradients. It's a much nicer problem to solve. And you can just solve it with, like, at least in principle, you can just solve it with off-the-shelf convex optimization solvers. Maybe you might have seen more commonly this lasso form. It's essentially like a Lagrangian form of this second line. So instead of having this as a constraint, we could just have like a weighted objective, minimize the weighted sum of sort of how well the x that you got fit the measurements, and this proxy for how sparse it is, so the one norm. And this lambda sort of controls the trade-off between being sparse and having a good fit. Of course, it's not all about optimization methods. Greedy methods like orthogonal matching pursuit have also been quite popular. So that's sparsity. So what do we do if we have a generative prior? And so we'll need to talk about like how we incorporate that generative prior assumption. It'll basically be sort of like the structure I showed you earlier, mapping a low dimensional K to a high dimensional N. So we're going to assume that X is in the range of the generative model. So yeah, this generative model, as you vary the input, it produces all sorts of outputs. And we're going to, our modeling assumption, instead of sparsity, our modeling assumption is that there exists some Z that produces the X that you're trying to recover. And for the most of the part, we'll say that there's like, it's exactly in the range of the generative model. So there's some Z that exactly produces your unknown X. But of course, we could easily adapt that to say that it only holds approximately. We can allow a bit of representation error. So when that's the case, there's basically a natural counterpart to this convex relaxation, but things are sort of flipped around. So instead of minimizing your sort of structural term subject to fit, we're going to swap that around and say, let's minimize the fit, like let's get as good fit as possible, subject to our structural assumptions. You could do the same with sparsity as well. You could minimize this subject to a certain sparsity level. And that's essentially the type of thing we're doing here. Minimize, get the best fit possible subject to being in the generative model. Unfortunately, that could be very difficult to solve again, a bit like how this minimized sparsity was hard to solve. Because your generative model is a very complex object. It's this neural network full of nonlinearities. If you try to like picture the landscape, it's going to have all sorts of local minima and so on. But these days in machine learning, people don't seem to be scared of non-convexity and NP hardness anymore. So yeah, even when you have this worry about will you actually find the global minimum, today's attitude is generally just, well, let's try anyway. Let's run gradient descent, and let's hope that we don't get stuck in too bad of a local minimum. And it will turn out that in practice, this does work very well. Often people need to do a few random restarts just to reduce that risk. But yeah, on typical networks, it doesn't seem to be a major issue. Like the fact that you may only get to a local minimum doesn't seem to hurt us too much. There have been some other methods proposed apart from just gradient descent in the Z space. So people have also proposed to do gradient descent in the X space. So like sort of directly doing gradient steps over X. The problem there is that you might like move too far away from the signals your generative model is representing. So you sort of alternate between that and projection. Projection brings you back to the range of the generative model. And so if you alternate between these X gradient steps and these projections, that can work very well as well. So this is not our work so far. This is from an influential paper by Bora et al. 2017. I think it was ICML. And I'll show you some of the numerical results from their work, which do highlight that, yeah, you can really get away with a lot fewer measurements compared to sparsity approaches if you have an accurate generative model. So this is a compressed sensing task. Sorry, I didn't write out the exact details like number of measurements and so on. It's on the Celeb A dataset. And you can see that with the number of measurements given, the generative prior approach at the bottom, it's far from perfect, but it does do pretty well. Like it gives you a pretty reasonable reconstruction of the face, even though it's not perfect. And the sparsity approaches, it depends on what domain you work in. You could be sparse in the Fourier domain, which is the second row, or sparse in the wavelet domain, which is the third row. But basically, sparsity is not capturing enough. It's not capturing a fine-grained enough information about the data that we're working with. So with this number of measurements, it really fails quite badly. They also have experiments for other tasks. This one I didn't show the sparsity-based approaches. I just showed the generative ones here. The original image, blurred versions, and deblurred. Again, not always perfect. Like you can see the mouth changes here, but it does do a decent job. And this is from 2017. Naturally, things have only improved from there. There's, for example, some very nice papers at this year's ICML from the same group, Alex Demarcus, the group of Alex Demarcus. We can also look a bit more quantitative. So we could say, like, as we vary the number of measurements, how well do these methods perform? And where the generative prior assumption really helps a lot is with fewer measurements. I think these pictures might have been with like roughly 50 measurements, whereas the number of pixels is in the thousands. So yeah, with fewer measurements, the reconstruction error quickly drops. Whereas the sparsity-based methods, this top one is lesser. It starts off very high and then drops a fair bit later. Like it drops around 200 to 400 measurements rather than like 25 to 50 measurements. Left one is MNIST and right one is Celeb A. Maybe not quite as much of a gap in Celeb A, but still a pretty striking difference. Those who are very observant may notice the very bottom corner of the plot. You'll notice that eventually these generative prior methods saturate in how well they do. And this returns to the problem I mentioned earlier in that generative models don't necessarily capture everything that you expect to observe. So they just sort of learn from a training set, but of course, training and test images are not exactly the same. So when it comes to test images that weren't in your training set, maybe your model will not actually will not actually generate them perfectly or will not actually represent them perfectly. So there's this side issue. Like if you have really a lot of measurements, the generative prior techniques can saturate, whereas the sparsity ones get better and better and basically get to zero. But again, this is from 2017, and there have since been improvements to get around this. A first work proposed to combine generative and sparsity assumptions together, so you have both. And other works have done things like using invertible neural networks, which can overcome representation issues. Okay, so now I'm going to move on to theoretical analysis. And I'm going to impose some assumptions, which may seem a bit restrictive, but most of them were actually relaxed in this 2017 paper. So to keep things simple, let's say that the generative model exactly represents the signal you're trying to estimate. And let's not worry about optimization error. Let's say that this objective that you want to minimize can be optimized perfectly. We'll also focus on Gaussian measurements because that's most convenient for the theory. I think this is the most restrictive assumption, which it would be nice to relax. And we'll also assume Gaussian noise, which is quite convenient. In our work, we're going to be focusing actually on algorithm independent lower bounds, sort of hardness results saying that no algorithm can do well if you have too few measurements. So actually, when it comes to lower bounds, these assumptions mostly only make the results stronger. In the lower bound, we also will not assume Gaussian measurements. So these things like no representation error, no optimization error actually make the lower bound stronger because they give a statement like, even if you have these ideal assumptions, this hardness result still holds. In the upper bound, these assumptions would be restrictive, but the paper actually relaxes them all. We also need to mathematically say like what sort of generative models we're interested in. We can't just have an arbitrary function G because an arbitrary function could be arbitrarily ugly. So the types of generative models that this paper proposed was Lipschitz continuous. So you can have any function at all as long as it's Lipschitz continuous, meaning small changes in the input lead to small changes in the output multiplied by at most L. The other type of model they considered was, let's just say it's a neural network and it's ReLU, and the complexity is controlled by the width and depth of the neural network. So we'll start with this first one, Lipschitz case, and then we'll move on to ReLU neural networks. I'm stating a simplified version of their upper bound. So yeah, it's simplified with all these assumptions, but you can see that paper for the more complex version. And essentially it says that if you have an L-Lipschitz generative model, if you want to bring your estimation error down to like the noise level, I'm just letting alpha be sort of the level of the Gaussian noise added. The number of measurements is basically k log L. There's some other terms in the log, but L is by far the most significant. So essentially k log L is the complexity of their upper bound. That's for spherical domains, and for rectangular domains, there's like an extra factor inside the log. But essentially it's the same kind of result. It's just that rectangles have a higher volume than spheres, which is why you get a bit larger term inside the log. So this is interesting because there's actually no dependence on the ambient dimension, n. So it's actually only the Lipschitz constant that matters. The ambient dimension could be as large as you like, and the complexity doesn't increase, or at least the only increase would be via L increasing. And this is in contrast to sparse signals. Typically for sparsity, let me use S for the sparsity to avoid confusion. For sparsity, typically, like I said, would be S log n. So it may not sound that different, like log n versus log L, they're both just log factors. But the bigger gain of generative models is not the log factor. The bigger gain is like what this K and S are actually representing. And the point is that a generative model with K inputs could much better represent your data than sparsity with the same number of coefficients. That's really where the gain is, from better modeling with the same number of parameters, rather than by improving the log factor. Okay, so like, as I said, the half of this talk will be in our own work, and it will be focusing on our algorithm independent lower bounds, talking about our lower bounds are basically trying to show that the upper bounds cannot be improved unless you impose further assumptions. So our lower bounds are saying like, no matter how clever your recovery algorithm is, no matter what measurement matrix you use at least up to like natural constraints, you will not be able to improve this result for general choices of the generative model. So the result is here. There exists a Lipschitz continuous generative model such that if you get the same guarantee, you must have that above number of measurements, at least up to constant factors. So big O and big omega are just hiding constant factors. We haven't pinpointed the constants, but we have at least pinpointed the scaling laws. And same for rectangular domains. The upper and lower bounds match in that case as well. Just to be clear, we're not saying that no matter what generative model, it's going to be that hard. We're just saying that at least for a worst case generative model, it will be that hard. So yeah, essentially, maybe in some cases you can improve the upper bound, but if you want to improve it, you'd better be assuming more than just Lipschitz. You'd better have extra assumptions, which somehow reduce the complexity. If you just assume Lipschitz, then you get this lower bound, which says we can't do better. I'll just very briefly give the upper bound proof outline, which some of these techniques may be familiar if you've worked on like compressed sensing with sparsity. So again, G is a mapping from low dimensional RK to high dimensional Rn. And the proof uses a covering argument, which is very common in compressed sensing. So we try to cover the input domain with enough points such that any point in the domain is within delta over L of the closest cover point. So yeah, you can imagine trying to cover points over a sphere. You might need a lot of points, but we can control how many points you actually need to do that. Once you cover the input, we can use this Lipschitz property to say that actually we're also covering the output. But the distance parameter blows up by L because of the Lipschitz. So that's sort of why we divided by L here, so that we can blow it up by L and everything will be within distance delta. The number of points needed to cover a sphere is very well known. This is like a very standard result. It's roughly like LR on delta to the power of K. So when you take the log, or like, yeah, I guess it's exponential of this log term. When you take the log, you get K log LR over delta. Okay, so why is that useful? Because once you've got a covering, you can use the fact that Gaussian measurements preserve basically like geometric properties of any finite set of points. And the number of Gaussian measurements you need for that preservation is log of the number of covering points. So like log of n, the log basically cancels out with the exponential. And that's why the number of measurements we need is like this K log L. This is the restricted eigenvalue condition, which is a lot like the restricted isometry property you might have seen in compressed sensing. And skipping over many technical details, once you've shown this restricted eigenvalue condition, it's a fairly standard procedure to show that like minimizing this loss, this squared distance, gives you something which is not too far from the true X star. Okay, so I went over that pretty quickly, but of course, details are in these authors' ICML paper. I'll also give you a bit of an outline of our lower bound. And the idea is conceptually quite simple, actually. We only want to show a lower bound for a worst case Lipschitz generative model. So we can actually choose whatever generative model we like to generate some signals we believe to be hard to recover. And we first tried this on some signals we didn't expect to be like the hardest possible case. Like we expected we'd get some lower bound, but not necessarily a tight one. And we were then a bit surprised when what we got out actually matched the upper bound. Because what we did was quite simple. We just said, let's create a generative model that creates sparse signals. And it wasn't quite arbitrary sparse signals, but it was like group sparse. Here I've divided signal into 4 groups, and I've put a single non-zero coefficient in each of the groups. There's been some other work showing you can generate general sparse vectors with a generative model, but we found this group sparse idea to be a bit easier to work with. Okay, so these groups are of size n over k, and there's 1 per group. So the number of non-zeros shaded in black here is k, as we would like. How do we create a generative? How do we create a function that actually generates things like this? Is quite simple. We map. Remember, our input is of length k. So our first input we map to the first block. Our second input we map to the second block, and so on and so forth. And they all map in the same way. So this is an illustration of how we map Z1 to elements of this first block. If Z1 lies in this range, then we get what's shown here, like the first entry being non-zero. If Z1 was here in this second part, then it would be the second one that's on, and so on. If it was the third one, it would be the third. And we could just sort of shift these across the whole domain. So here's the region where it would be the first one. Here's where it would be the second one. You notice that these are all disjoint, and they eventually cover like all the way from left to right. So yeah, very simple function. It's certainly not any sort of practical generative model you'd be interested in, but we're just doing a theoretical analysis for the worst case generative model, so we're allowed to use this. Because this is so simple, this is just like a few straight lines, we can very easily get the explicit Lipschitz constant. It's just like the slope. Like we can read off the slope immediately based on the parameters that we've set. So the Lipschitz model, the Lipschitz parameter, we can control basically trivially. And when we set the Lipschitz constant in the right way, and we set the sort of parameters in the right way, we apply statistical lower bounds from group sparse recovery, which is like quite standard. Again, skipping over all the technical details, we're lucky enough that this ends up giving us the tight result. So yeah, the statistical group class analysis is very standard. We gave like a one-page proof based on Fenner's inequality. I actually received a helpful email today saying that perhaps we didn't actually need to do that. There was a work in 2011 we were unfortunately unaware of, which gave lower bounds for group sparse recovery. And I believe they even gave much stronger in a certain sense, lower bounds than the one that we derived in our paper that I'm talking about. But the weaker one that we derived was sufficient for what we needed. Okay, so I think that's the end of the outline for Lipschitz models. And then I'll move on to ReLU neural network models. Again, I'll just pause for a second in case there's any questions. Okay, so in this Bora et al. Paper in 2017, they also gave theory for the case that there's no constraints on there's no Lipschitz constraints. It could be the Lipschitz constant could be arbitrarily large, but they replaced that by a different assumption because you have to have some kind of assumption to make this tractable. And their assumption is that your network is a ReLU neural network. So hopefully most of you have seen ReLU neural networks before. This is an illustration of a single neuron. A neuron takes all the inputs, multiplies them by weights, and passes them through a nonlinearity. This now famous nonlinearity is the ReLU. Just clip the negative part to 0, keep the positive part as the identity. And a ReLU neural network has many, many neurons. They can be combined in all sorts of different ways. This is just like don't read too much into this architecture. This is just an arbitrary illustration. But yeah, basically all these different layers take the previous layer, pass it through a bunch of neurons to get the next layer. And if you do that again and again, you get this very complex structure. If you train this structure using data, then we have all these amazing modern machine learning results. And this illustration is quite generative because it's like associated with generative because it starts with a low dimensional latent and expands it into like a higher dimensional, let's say an image. The most famous is probably generative adversarial networks. There's also things like variational autoencoders, but we don't need to worry much about the specifics here. Okay, so theoretical results for the ReLU case. The complexity in this case is controlled by the width of the network, which is basically width is maximum number of neurons per layer, and also the depth of the network, which is the number of layers. So the number of measurements comes out from their paper to be K still appears as the leading coefficient, but then it's also multiplied by depth and log of the width. And the guarantee is like before, like bringing the estimation error down to the noise level. And in their paper, again, they give a more general result. And this is morally quite similar to the one about Lipschitz, because the typical Lipschitz constant for a ReLU neural network is actually W to the KD. May have made a mistake there. Maybe I should have said W to the D. So yeah, sorry, W to the D, so that K log L becomes exactly KD log W. Okay, so cross out that K, sorry about that. Our lower bound was a bit more of a mouthful, like might be a bit less easy to grasp immediately. But basically we gave a lower bound dependent on some generic parameters, which we called N0 and K0, some sort of auxiliary parameters. And we showed that given such parameters, we can construct a generative model such that the number of measurements must be at least this lower bound, K times K0 times the log term. And we showed that this generative model can be implemented as a ReLU network in multiple different ways. The two most extreme cases are we could have a shallow network where the depth is 2, so only 2 layers, but a very large width. So sort of this exponentially growing width. Or we can implement it as a very deep neural network, but with a much lower width. So in that case, the depth is this K0 times the log term. And we actually also handled all the cases in between. You could be like moderately shallow and moderately deep. And the paper gives similar results in that case, but I'm just focusing on the easiest to understand. So yeah, it's a bit harder to directly compare, but we can basically ask, if we apply these depths and widths in the upper bound, how does the scaling compare? And in the shallow case, the scaling actually matches exactly. So if for the shallow neural network, the upper bound, plug in the depth and width, you get the exact same upper bound matching the lower bound to within constant factors. So again, order optimality. In the deep neural network case, we were close, but not quite there, because we had an extra log factor. So not quite order optimal, but at least optimal to within a single log factor. And in the in-between cases as well, in the moderately shallow, moderately deep, it was in between these, and it was like basically always tight to within at least a log factor. Again, an outline of the upper bound. It's along the lines of the case of Lipschitz models, but it's based on counting linear regions. Okay, so there's this, I think it was known before this paper that a ReLU network partitions the space into linear regions. Like a ReLU may be very complex, but ultimately it is just piecewise linear, just with many, many pieces. Basically, the number of pieces is like W to the KD, and the log of that is what dictates your number of measurements, sort of by these similar things I mentioned before, like oblivious random breading or Johnson-Lindenstrass, which makes the complexity be log of the number of linear regions. That's the very rough intuition behind the upper bound. The lower bound is, again, along the same lines as the Lipschitz case, but a bit more complicated. So this may be a bit tough to grasp, but with the Lipschitz case, we were generating directly like k-sparse signals. And here we actually like generate not k-sparse, but k times k0 sparse. So we sort of use the same idea of doing k things in parallel, but each one of those is not generating a single non-zero coefficient. It's generating multiple non-zero coefficients, which is dictated by this k0. And we did that using a recursive structure. So sort of the outermost recursive part is using the same idea as what I showed you in the Lipschitz case. If your Z entry lies here, then the first entry will be on. If it lies here, the second entry will be on, and so on. But then we sort of recurse this idea within these like regions. We sort of, yeah, look within this narrow region and repeat that idea. We have this first region, which is very, very narrow, then a second region, and so on and so forth. And then we actually go even further. It's getting so narrow that I can't even draw it, but we imagine going even further and even further, k0 times, so that, yeah, this outer one dictates one block, this second outer dictates the next block, and so on down to the last block. And then we have yet another layer because we're doing all of this k times, and that's what gives us k times k0 blocks and a k times k0 block sparse signal. This is a bit of a misleading picture because we can't implement these vertical lines using a ReLU, but we can like basically approximate rectangles by trapeziums arbitrarily closely, and that's not a major issue. From there, we can sort of count the width and depth of the ReLU neural network needed to produce these sorts of signals. For the high width case, it's pretty easy because for shallow neural networks, the number of neurons is just dictated by the number of pieces in the piecewise linear signal. So like it's like 1, 2, 3, 4, 5. That would be like 5 pieces, but then of course there'll be more pieces here. We can count the number of pieces in the piecewise linear model, and that gives us our neural network width. For deep neural networks, we have to be a bit more intelligent, but luckily there's this very nice work of Telegarsky, which gives you methods for creating periodic signals using deep neural networks. Notice that these signals here are periodic. And briefly, you can generate 2 to the power of d repetitions using a depth d neural network. And that's why when it comes to depth, it's kind of like the log of the number of repetitions is what's relevant. Whereas width, it's like the actual number of pieces. So there's this important distinction between width and depth. depth in some sense can be much more powerful than width. Okay, so that's maybe a lot to take in, but once it's done, we again have a generative model that produces sparse signals, and we could just use normal minimax statistical analysis to get our lower bound. And that's how this proof works. Okay, I think that's about all I wanted to say. Just a bit of a brief note on our more recent work. This talk has all been about linear inverse problems, but not everything in the real world is linear. So we had a paper on 1-bit observations, and we weren't the only, we were not the only ones. There were a couple of other nice works on this as well. Again, basically with k log L being the upper bound. I believe the lower bound is still open for the 1-bit case. And we looked into more general observation models. You need to make a few more assumptions there, but again, you can get like the k log L type of scaling with Gaussian measurements. Here is some reading. So the first half of the talk was mainly around this initial paper by Bora et al., Alex DeMarcus's group on in ICML 2017. It's been very influential. You can go to Google Scholar and click cited by to see who cited that work and who's built upon it. This is the link on our lower bounds, which was the second half of this talk. It was published in Selected Areas in Information Theory. I should also mention there was some concurrent work by Eric Price's group. And they used fairly different techniques to ours based on reduction to communication complexity. So yeah, very nice, like complementary techniques, which have their own advantages as well. I believe they only focused on the Lipschitz case and not the ReLU network case. But on the other hand, their paper also went into like more detail in other aspects. So definitely have a look at that if you're interested. And these are just those last two works on nonlinear models that I mentioned. Okay, so that's the end of my talk, and I'd be happy to answer any questions.